Hello guys, this is Michael Sinenko, and in today's video I'm going to be evaluating the indefinite integral of the square root of tangent of x dx. This is a very difficult integral if any of you have ever tried this. It seems like there's a lot of unconventional ways that you wouldn't necessarily be able to use, or at least you would have to modify those conventional ways of solving integrals, such as u substitution or any kind of variable substitution, and of course all the steps that would be required after that, like taking the derivative and whatnot of that variable and then plugging back in. All of those kind of techniques are going to be utilized, but they're going to be modified. And what you're going to realize when you do this integral is there's going to be some steps in here which are very counterintuitive. They're not exactly steps that people would normally think of, just on the fly. That this kind of integral is quite honestly like a type of art form of math. But in those areas, I will definitely explain to you why we are doing the things that we are doing. So the first thing that we want to do with this integral right here is we want to just do a certain kind of substitution. You could do a u, v, x, y, phi, whatever, but I'm going to do a t substitution. You can use u is the convention, so if you have a t, and we can say t is equal to the square root of the tangent of x. And then we can take the derivative of this. So if you guys remember from derivative rules, this is going to be utilizing the chain rule right here. So the best thing that you can always do is with these kind of integrals is make that square root to the half power, bring the half out front, and then subtract by 1. What ends up happening is you have 1 over the 2, and then you have the square root of tangent of x, and then you take the derivative of the inside function, which is going to be times secant squared x, and you have all that with respect to x. Now what I can do here is I can actually clean this up a little bit, and that's just to show you what's going on with this. So you have the secant squared of x all over 2 times the square root of tangent of x, and all of this times dx right here. And that makes sense, because you take the 1/2 out, or for right here, and then using that power rule, basically you bring in the 1/2 in front, and then the 1/2 minus 1 would be negative 1/2, and then we know from our exponent rules anything raised to the half is 1 over that, and then put that back into the denominator, so it becomes a positive 1/2, becomes the square root of that. And then the derivative of the tangent of x is the secant squared of x dx. So what we can do now is if we take this whole entire piece right here and we multiply by the reciprocal of what's right here inside right here, then we can isolate dx on this side and get this in terms of t, and then we can plug in what's on this side, which is equal to the dx term for dx right here. So if I was to multiply all of this by the reciprocal, then what would end up happening is it would be 2 times the secant, or not 2 times the secant, my bad. It would be 2 times the square root of tangent of x all over secant squared of x, and then all that would be times dt, and this would be equal to dx, because if you were to multiply right here, all these would cancel out. Well, then what we see now is this is all equal to dx, like I was just saying, so all of this can go in for this dx. So we have the integral square root tangent of x, and then times 2 times the square root of tangent of x all over secant squared of x. And then what we can have here is just our dt term. And now that we don't really need this anymore, we can get some time, space made out. Well, what we can see here automatically is when you multiply the square root times the square root, it is of the same function. It is the same thing as that function. In other words, if you had the square root of x times the square root of x, that's just equal to x. And the reason why that is if you have this to the 1/2 times x to the 1/2, then what you're basically doing is you're adding those two exponents, and then 1/2 times 1, or 1/2 plus 1/2 is x to the 1. Well, that same principle applies to the square root of tangent of x. So we can basically go and turn this integral into 2 times the tangent of x. And we can actually also leave that secant squared of x dt right here. All right, so what can we do next now? So what we can do is we can use our knowledge of trigonometry and different kind of trigonometric laws, and any kind of like manipulations, right? For example, like you have that one formula where it's a sine squared of x plus cosine squared of x is equal to 1. And this is just one of the identities that is known from trigonometry. And you can actually manipulate this by either dividing this whole entire equation by sine squared or cosine squared. Well, what's useful for us is we have a tangent right here and we have a secant right here. And if we were to divide this whole entire equation by the cosine squared of x, so this one divided by cosine squared of x, this one divided by the cosine squared of x, and this one as well, cosine squared of x, well, that's going to give us our tangent term, tangent squared of x. This is just going to be 1, and 1 over the cosine is always going to be the secant, but this is a squared term, so it's secant squared of x. Look at that. So all of this is equal to secant squared of x. So what we can do is we can plug that in right here, and that can allow us to simplify further. So what I can do is just erase this out and actually put the tangent x squared plus 1. And we don't need this anymore. What we can do now is we can furthermore basically simplify this some more. So we have the tangent terms here. What can we do? And we know that our t is equal to the square root of tangent of x. Well, the interesting thing is that if you have the tangent of x and it's squared, if you were to square that, it'd be the same thing as equaling to just the tangent of x, because the square undoes the square root, because it's the same thing as what I was saying earlier. It's when you square something, it's that that variable or whatever or number being multiplied by itself, and that gets rid of the square. So if you had like the square root of x times the square root of x, it's x. Same thing with here, but now we're just squaring it. Well, so it's just equal to this. Well, we can just say that t, it's equal to t squared, because t is just that. So if you do one thing to one side, you have to do it to the other side. So in this case, we squared the tangent of x term right here to be able to get it to just be tangent of x. So we have to do the same over there. So we can actually turn this into 2 times t squared. So if I remove all that right here, 2 times t squared. We could also do the same thing for the bottom there. Well, we now need this to be squared. Well, if I want to square this, I need to square this again. So, and if you do this right here and you square it, that's the same thing as multiplying the powers. So that becomes 2t, t to the 4th, t to the 4th. And then you have to do the same thing here. And this is the same thing as taking this and raising that to the second power again. So that's what that is. So that this right here will give you that, which basically means that you will have the t to the fourth. So I can do the same thing here. I can say that this is going to be t to the fourth plus 1 dt. And now that we have that taken care of, we can actually remove all of that. So what can we actually do here next? All right, so what we can do now is we can actually go into that part of the video that I was describing, which is kind of counterintuitive. And you'll be asking, why are we doing this? But it'll all make sense when I explain it to you step by step. This wasn't exactly my method of doing things, but it's the way that I figured, and I think it's very, very interesting. And if you ever come across something like this, then you'll have, like, I guess, a mental toolbox of things that you could possibly do to manipulate an indefinite integral or definite, and be able to evaluate an answer based on those types of manipulations that you can utilize. All right, so what we can do here is, I'm just going to write an arrow right here, is we can break this up and say that 2t squared is the same thing as t squared times t squared. The basic algebra that we know, because if you did t squared plus t squared, it's 2t squared. Well, what we can also add here, and this is the weird part, bear with me, is you can do a plus 1 and a minus 1 here, and we'll just have that t to the fourth right along, plus 1, and this is all in respect to t, dt. So now the reason why we do this is it's like a form of partial fractional decomposition. You know, it's a variation of that. I don't know necessarily what the exact term for it would be called, but it is a type of partial fractional decomposition, because what we can do here is now we can group one of these t squared terms with one of the ones and then the other one with a minus 1. So what we can do here is write this integral as t squared and then plus 1 all over t to the fourth plus 1 dt. And then we can add that to the t squared minus 1 all over t to the fourth plus 1 dt. All right, so let's just actually get rid of this so we can get some more surface area here. And next, what we can do is we can actually divide by the lowest term of t here to simplify our expression here. And you'll see why we're going to do that in this step. So this ends up becoming, if I actually rewrite it right here, so we basically do t squared all over t squared plus 1 over t squared all over t to the fourth all over t squared plus 1 over t squared. And we do the same thing for the other one. And this is respect to dt. And we still have our integral. We haven't integrated yet. So we do the same thing, t squared over t squared. And this would be minus 1 over t squared all over t to the fourth all over t squared plus 1 over t squared dt. And then, of course, we can break all of this down. Makes sense, because the t squared over t squared is going to be just 1. So just doing this one right here, this becomes 1 over t squared. Well, this one, you just lose one of the powers. You do 4 minus 2. That's what we learned from algebra. And then this will just be 1 over t squared dt. And then you do the same thing over here. It's essentially the same thing. You just have that minus sign right there. So if I was to base, or, well, look at that, I just said it and I did it anyway. So 1 minus 1 over t squared all over t squared plus 1 over t squared. And that's with respect to dt. And again, I'm going to remove this since we have it down there. Y'all can see it. Now, what we can do next here is we're going to actually add some other terms here, and you're going to wonder why we're doing it, but the reason why we're doing it is because we can utilize this algebraic formula here, which basically says if you have a squared plus 2ab plus b squared, you basically have a plus b squared. And then if you have a squared minus 2ab plus b squared, you have a minus b squared. And that's going to be very, very useful for us here in a second, actually. What we can do with this, since we know this 2 is in here, we can actually use the fact that this 2 is here for turning this expression down here into a form like this. And the reason why we want to do that is because this right here is very similar, because when you square 1, it's 1. And over here, if you just square the numerator, it's still going to be 1. But here, the denominator, it's going to be squared. So if you had this like 1 over t, then if you just squared it, then you have 1 over t squared, obviously. So how do we actually add that to be useful? Well, we can basically say that on this side we have plus 2 minus 2, because it has to be 0. You can't just add random stuff to it. Well, you can, but it won't help you. So plus t minus t, 2, not t. Plus 2 minus 2. So what we can actually do here now is we can basically group this, where we could just add that minus 2 to the end, but then basically here, got this eraser here, is remove this for a second so I can rewrite it and do t squared minus 2 plus 1 over t squared minus, or plus 2, and then do the same thing over here. And this one will be plus 2 plus 1 over t squared minus 2. And this right here can actually be broken down utilizing these formulas. And you're going to see that here in a second. How so? Well, since this one's just really close and it'll make sense, why don't I just do this one for this? Well, the thing is if I rewrite this right here, t squared plus 2 plus 1 over t squared, well, this can be a and this can be b for our formula right here. And how does that make sense? Well, if I had just a, which is just going to be our t, and we had our b right here, which is going to be just 1 over t squared, it makes sense. Why? Because if I was to expand this from algebra, we know that we would be 2 times that would be t squared plus 2 times a times b. Well, the thing is, if I have plus 2 times a, which is t squared, and then b, which is 1 over t squared, we would also have the plus b squared. Well, 1 squared is 1, and then t squared is 1 over t squared. And look at this. This cancels, that cancels, and then it's just plus 2 times 1. You know what I mean? And it wouldn't matter if this was squared or not squared, because if it was just t, and this was just t, it'd still cancel, or t to the fourth or t to the fifth. So in this, you would want to make sure that you're keeping things consistent with the formula, but in this case, it worked out that way. I should have actually said it was 2 times t all over 1 times t, 1 divided by t. And then that would have made sense because this was a squared, and then we're actually taking the square root of that, which is going to be t, in order to get our squared term. And then the same thing follows for the other formula for over here, and that's where we would get that minus from. So that right here, this would be able to go in for this. So you'd be able to take all of this and just do t plus 1 over t, square that, minus 2. And then this one, it would be the same thing, just be t minus 1 over t squared plus 2. Interesting, interesting, interesting. Now, what is it that we can do, guys? What is it that we can do here? Well, why don't we actually do another substitution? What we can do here is we could substitute again, and we can do whatever variable that you would want. Z, V, whatever. I'm just going to choose Z, and it doesn't matter. It's just a variable to do a substitution. So if I did Z, and I'm going to say this is Z1, so I'm talking about this integral right here, and this is the second integral. If I say Z1 is equal to t minus 1 over t squared, or not, let's not do the squared part, let's just do what's inside of the parentheses, obviously, here. And then what we do is we're going to differentiate this like we normally would. So dz1, well, the derivative of t is just 1. And then we can also take the derivative of this, and then if we utilize the rule right here, so d df, where that's the function of 1 over f, is the same thing as ddf of f, and this is going to be just f squared. So, and all of this is actually also minus, so or equal to minus that. Well, the derivative of f is 1, and that's where we're going to get the 1, and then f is just f squared. It's the bottom squared right here, and it's going to be minus. So in our case here, we're going to actually have this minus come out, and it's going to be negative 1 over our function, which is t squared, but there's going to be a minus right here. So if I put this over here, it would be minus 1 over t squared. The minus and the minus become plus. So what I can do is just write that in its final form here as plus 1 over t squared. And we're going to also do the same thing for this other side. So it's going to be t plus 1 over t. And if we took the derivative of this, dz sub 2, same thing was going to happen, but it's going to be a plus and a minus, because using that rule right there, the differentiation rule, which kind of skips the quotient rule of calculus. You could utilize the quotient rule, but that's another way of doing things. You can look it up. It's somewhere out on the internet, but it would end up being the same thing, but it'd be plus minus. So that would be just minus. So it would be 1 minus 1 over t squared. And of course, I can't forget these are respect to dt. This is in respect to dt as well. Well, the interesting thing here is is I can do the same thing, isolate, divide all of this over here under dz2 and do the same thing over here for dz1, and then you're going to end up isolating the dt right here, and then all of what's on that side is going to be equal to dt. Well, what I can do here is remove this dt, and I'm assuming that most people here are pretty formidable with algebra, so I don't have to write everything. I don't have a whole lot of space. That if you move this over, it would just be 1 over that. So it would be 1, you just take, this is like times that, 1 over the 1 minus 1 over t squared. And this was going to be dz, and I'll just leave it as dz. That was just for the sake of organizing things. Well, what do we immediately notice here is, since these are being multiplied together, check it out. This can disappear, and that can disappear. Lovely. So we're actually, all we're left with is what's here at the bottom. And the thing is that we can actually replace this with z, because that's what that is, and this becomes z squared. So it becomes z squared minus 2. We already said that those cancel, and it's just 1, let me write that 1 better, dz, because we're in the z world now. And the same thing applies here. The same thing is going to happen here. So I'm going to skip that ahead. Same thing is just going to have like a minus right there. Here, we're going to say that this right here is equal to this, but it's z1 squared, but we're just going to keep it as z, you know? So this will be z squared again, and this will be plus 2 dz. That's our new type of integration, our new integrating variable. And that's what where we're at now. All right, now this is the moment that we've actually been waiting for. We've been carrying this integral along so much just because we've been doing so much algebraic manipulation underneath or within the integral itself. Well, there's actually a formula that we know for both of these right here. And for the first one right here, the z squared term, we know the following formula. We know that if we have the integral of 1 over x squared plus a squared dx, we know that that is the same thing as 1 over a times the arc tangent of x over a plus c. And then what we can do is we can actually put that in for here. So this is our x, and z is our x, and 2 is our a squared. Well, 2 is already the squared term. That means we can take the square root of that, and then the square root of 2 times the square root of 2 would be this, which is that squared. So we can actually put the square root of 2 in here. Same right here, the square root of 2. And then x, it's not x squared, it's going to be z. And that's what we have. And then the plus c was going to come out at the very end once we integrate everything. So the other formula that we have here that we can utilize for this, it's going to be in terms of like a natural log. So this one, there's the following formula. Let me actually do it up here. The integral of 1 over x squared minus a squared dx is equal to 1 over 2a times the natural log of the absolute value of a, or x minus a, should I say, x minus a all over x plus a. And of course that's going to be plus c. But for our sake right here, this is what we're just going to have right here. And what we can do is we can actually do the same thing. Here it's just going to be the square root of 2. The x is going to be z. Z. And then our a, of course, is the square root of 2 again. Square root of 2. And that's what we have so far. So we can actually now combine these two together and actually simplify from there. All right, so what we can do is actually remove some of this stuff that's in our way. Plus c for our constant of integration. But we're not done yet. Our z was defined, if you remember. Now, this side and this side are going to be a little bit different. We said on this side, it was that integral where it was 1 over a minus, or x minus, x squared minus a squared. And this side it was the 1 over x squared plus a squared right there. So on this side, we ended up saying that it was 1 over 1 minus 1 over t. Remember? And then we squared that. And the reason why I remember that is because what ended up happening, if we had the minus and the minus, that was the plus, and that allowed that to get rid of that there. So this was the 1 over 1 minus 1 over t. And I can also make sure to just check. Actually did make a mistake. It's 1 plus in this case. So 1 plus would go into here. And if I kept it on the board, I would have seen in a normal situation, you're doing math, you're going to see what you're doing, and of course just reference what you had derived earlier and then put that in for z, because we said that this was that z term. So in this case, let me just do this side first. 1 over 2 root of 2 natural log. This would be that 1 plus 1 over t minus the root of 2. And this would be same thing, 1 plus 1 over t plus the root of 2. And on this side, if one of them is going to be the t plus, so that the other one has to be the opposite then, just based by logic there. So this would be 1 minus 1 over t root of 2. And that's what we would have here thus far. Now that we're not necessarily done here yet. What we have to do next now is we actually have to see that the t, which I did keep on the board, is actually it's the square root of the tangent of x. So wherever these t's are, you just have to put the square root of the tangent of x. Luckily I have a dry erase here, so I can actually get rid of that here, right here, and put root of tangent of x, root of tangent of x, and then right here, root tangent of x. And that is essentially our answer here. Now you can simplify this, of course, you know, like rationalizing the denominator right here and moving this tangent over here, and then it's like the square root of tangent of x minus 1 over the square root of tangent of x, and then you could do further algebraic manipulation here to solve it. But I'm going to leave that for you guys to do if that's something that you'd like to do. But this is the final answer. The video's running pretty long anyway, but there you go. That is the answer right there. 1 over the square root of 2 times the inverse tangent of 1 minus 1 over the square root of tangent of x divided by the square root of 2 plus 1 over 2 times the root of 2 times the absolute value of the absolute value of the natural log of 1 over, or 1 plus 1 over the tangent of x minus the square root of 2 over 1 plus 1 over the square root of tangent of x plus the root of 2 plus c, and that is our final answer. Thank you.